Oh, geez. So thank you everybody for coming. It's a pleasure to have Silvia Sellán come and give a talk at our seminar. Silvia comes to us from University of Toronto, where she is in her last year. She's a student of Alex Jacobson and has worked in volumetric representations of surfaces and sort of has done both sides of breaking and putting things together. Is that right?
That's right.
Both fracture and reconstruction. Today will be on the reconstruction side, I believe. She has received a number of awards and recognition from the community. She's done tremendous work, and it's a pleasure to have her talk this day.
Thank you, Michelle. Yeah, hi everyone. Thank you for having me. Oh, I hear the echo. Yeah, so I started my PhD in 2019, so I've actually never done talks in person until now because it was all through Zoom. So it really is like very nice to be here today. So thanks to Misha, especially for inviting me. Yes, I will mostly talk about surface reconstruction, but since I haven't been able to go to places and talk about my research until now, I thought I would also start by introducing myself and the type of work that I've been doing. And then I'll go really into depth into my latest work that I'm most excited by. And also at the end, I'll try to pitch a few projects that I have in mind I don't have time to do. So stay tuned for the end where I'll give you a chance to collaborate with me. I'll phrase it like that so it sounds good, but really it's more me wanting to collaborate with you guys. So what I've been working on is geometry. That's why I use this very pretentious title for the talk. You know, how to capture shapes, how to store them, how to study them, how to transform them. These are some of the types of fundamental geometric problems that I've looked at in my research. So let me show you about one of these fundamental geometric problems. This is a joint work with Noam Eigerman from Adobe and my PhD advisor, Alex Jacobson. And it's a very classic fundamental geometric problem. Take a shape that is moving through space following a given trajectory. What is the region of space that is covered by this shape as it moves? This is called a swept volume, and it looks something like this. And in this paper, we use what's called a continuation method, basically just a fancy mathematical method to make the current methods faster and better. This was useful to Adobe because they want to use it for 3D drawing, but it's also useful for other applications like path planning. So if you're writing a spaceship, the spaceship wants to find out if a given trajectory will collide against an obstacle so that it can know whether to keep going with that trajectory or try a different one. So this is a classic geometric problem. The input is a geometric object and a path, which is also given geometrically. And the output is another geometric object, which is called the swept volume. So someone.
Whoever has their mic on, can you please turn it off?
Yeah, I think that's, yeah, thank you. Great, so I was saying this is a fundamental geometric problem. Geometry in, geometry out. This is a problem that if you're a mathematician, it's very interesting because it's very geometrically rich. And that's what I meant when I say that I've tackled fundamental geometry problems. I thought I'd give you another example. So this is another fundamental geometric problem that I tackled together with Jacob Kesten, Yansheng An, and my advisor, Alex Jacobson. You'll get tired of seeing his face around. The idea was, how do we smooth a shape such that we only smooth the concave parts of a shape, but we keep the convex parts the same? And specifically, we keep the triangulation of the convex parts. This can be useful, for example, to edit shapes. Or we pitched it as a way of simulating rust, because rust accumulates in concave regions, but it doesn't accumulate in convex regions. But the main application is that since our output is only smoothing the concave regions, then it strictly contains the input, which means that you can use it as a way of simplifying meshes for things like animation. So again, this is another fundamental geometric problem where the input is a geometry, the output is a geometry, and we do a lot of math in the middle to go from input to output. So those are two problems I worked on initially, but lately I've been moving away from this type of geometric problem into something that I call Geometry Plus. Now, Geometry Plus is not a subscription service where you pay $10 a month and you get a new triangle in the mail or something like that. It's much more simpler than that. Plus just means literally adding things up. So it's geometry plus something else. Combining geometry with something, some other field, in a way that's greater than the sum of its parts, so that we can look at new problems that we wouldn't consider if we looked at them individually, and hopefully new solutions that we wouldn't consider. So I thought I'll give you a few examples of what this geometry plus vision is before we jump into the one I care about the most today. So a prototypical example of geometry plus is this work that I did with Noam Eigerman and my advisor Alec Jacobson, where we looked at an idea from signal processing. So these are people that research how to capture audio signals or image signals from computer vision. They have this concept called compressed sensing, which is a way of very strategically sampling a signal so that you capture the dominant features, basically. So, they use it for audio, for images, but we thought, is there any way we could treat a surface as a signal? It's kind of like an image, right? Kind of like an image. If we just treat the surface as a signal, that's a bit weird because, if you start thinking about it, 0 height or 0 position doesn't mean absence. So it's a bit of a weird thing to treat as a signal. But we used the insights from geometry that we have, and we thought, well, what about a differential map of the surface? So what about the second fundamental form of a surface? Can we treat that as a signal and use techniques from compressed sensing to make it fabricable? In the language of geometry, we make it developable. So we looked at the second fundamental form, used a technique from signal processing, and turned the surface into a developable surfaces. This is a prototypical example of my idea of geometry plus, because we really couldn't have done this without combining these two things. So we needed to understand signal processing to understand what compressed sensing was, and we needed to understand geometry to understand that we needed to compress the second fundamental form of a surface to get a developable surface. So anyway, that's one example. Here's another one where we combine geometry with numerical analysis. The idea here, this was a joint work with Heng-Yi Chen, Mitchell Dombowski, and Alec Jacobson. The idea here is that if you show a mathematician a domain and you tell them to solve a PDE on that domain, they don't ask how you got that domain. But we come from geometry, so we know a little bit about how a domain is constructed, how it's modeled. So in this paper, we leverage our knowledge about how a given domain is modeled originally to solve a partial differential equation on that domain in a way that makes it very easy. So in the language of geometry, you solve a partial differential equation on an object without needing a whole mesh of the domain, instead meshing the components that made up the domain in the modeling stage. So here's another example where just someone who did numerical analysis would have started with the final domain. Just someone that did geometry would not have understood the challenge of solving a PDE on the shape. We needed to combine geometry plus numerical analysis to even phrase this problem and to solve it. Here's another recent one. This is one I'm particularly proud of. So here we combine geometry with algorithmic fairness. This is a joint work with Anna Dodick from MIT, Professor Stat Kim and Amanda Phillips. And we looked at algorithms from our field, specifically the ones that output human geometries, and studied how they currently treat gender as an algorithmic variable. Spoiler, not great. And we looked at the harms and biases they introduced by doing so. This was, again, a project where you need to really understand what these geometric modeling algorithms are doing, but you also needed to really understand the field of algorithmic fairness to do this work. So this is another great example of geometry plus. Finally, another recent project I've worked on is this, where we use geometric insights to solve a classic physics simulation problem. This is a joint work with Jack Long, Leticia Matos da Silva, Aravind Ramakrishnan, Yushun Yang, and my advisor, Alec Jacobson. And we look at breaking things and simulating how things break. And our idea was very simple. There's this thing you might have heard of called vibration modes. They measure the most natural ways that a shape has of vibrating or deforming. If you've done physics or math, you might have heard of this in the context of a single string or a drum, but in computer graphics, we usually define it for more complex shapes. So these, we know how to compute. What we did was a very tiny change in their formulation to define fracture modes, basically how an object an object's preferred ways of rigidly braking. We can pre-compute these modes for any given shape, like this spaceship. And once we've pre-computed them, we can simulate impact-dependent fractures. So these are fractures that are different depending on what the impact is. So earlier it hit the front, now it hits the side, it breaks differently. We're simulating these in real time thanks to the pre-computation that we're doing. So our pitch is that they can be used for video games where you need to simulate many fractures very quickly. I had a lot of fun working on this project because breaking things is very fun. There's a childhood satisfaction there. And there's another satisfaction in breaking things and not having to clean up after, because you're breaking them on a computer and you can break it 1,000 times very quickly. But it can be equally satisfying to put things together. And also in a computer, this is very easy to do because you just turn the video upside down, backwards, right? You play the video backwards, you see something being put together. And this is actually what our latest work is doing. So in this work, this was a very unexpected collaboration that I just did with a group with our robotics and machine learning groups in our lab. So these are my collaborators, Yunchun Chen and Ziyi Wu, who are students in the robotics lab in our department. They're advised by Professor Animesh Garg, and of course, there's my advisor, Alec, again. So Ziyi and Yunchun looked at our algorithm and they said, oh, so you have something that simulates fractures very quickly. In like a millisecond, we can break something. And for me, as a graphics researcher, I do that so that I can simulate one fracture in one frame of a video game. But a machine learning person sees that you can do something in a millisecond, and they think, well, if I have 1,000 seconds, I can do it 1,000,000 times, right? So doing something fast to me means doing something once very fast. For them, it means doing it many times in a reasonable amount of time. So that's exactly what they pitched to us, and we said, yeah, sure. It's just about running our method 1,000,000 times, and we got a massive data set that we then use to train current machine learning algorithms and benchmark them for the task of reassembly. So we generated a lot of broken things so that algorithms can learn to put them together. And it turns out they're pretty bad at it, as you can see here. And we think that part of the reason why they're pretty bad is that there was not a very massive data set to benchmark these algorithms. And we hope that by providing this data set, now more algorithms can be developed that do better on it. So anyway, this is a very unexpected collaboration that I did not see coming. So hopefully I've convinced you that this geometry plus thing, my rebranding, is an interesting way of looking at problems from geometry and other fields. And now I'm going to tell you about this other work. Oh, maybe I'll try to take that thing. There you go. So I'll tell you about this latest work. This is one I'm very excited about. I'm also very excited about some future work that I hope it inspires. So here, I propose reframing a classic geometry problem from the lens of statistical learning. And this is a joint work with my amazing advisor, Alec Jacobson. I didn't put his picture this time because it's just us, and putting one picture seemed a bit egotistic. So I didn't give him that satisfaction, but it's also with him. So the question is simple. Let's start with this point cloud. This is an oriented point cloud. So a bunch of points and normal vectors in space. And I'm going to ask you a question. This car here, does it intersect the surface described by this point cloud? Of course, it doesn't hit any of the points. So maybe you say no. But that's not entirely true. The point cloud is a discrete representation of what we assume is a complete smooth surface, right? So it's not as trivial. The question is, does the car intersect the surface that's described by this point cloud? And that is pretty hard to answer, right? You see a bunch of points there. You don't know exactly what the surface looks like between them. So how would I answer if it crashes against it? Well, the way I would have answered it, maybe the way that you would answer it too, is I would use a surface reconstruction algorithm. I would try to go from this point cloud to a fully determined surface, and then I would test if that intersects the car or not. And the one surface reconstruction algorithm I know, and I think almost everyone knows by now, is Poisson surface reconstruction, which you might have heard of. I don't know, it's by some cache thing guy. So the way this algorithm works is that it uses the point cloud to get a scalar field It looks like this, a scalar field that is negative inside the shape and positive outside the shape. And by that definition, the zero level set of this scalar field, the points that have value 0, is the reconstructed surface. So there we go. Using Poisson reconstruction, we get a surface. Does the car intersect the surface? Well, it doesn't, right? It's clearly outside of the Poisson reconstruction surface. So at least we can formulate an answer, according to Gaussian et al. It doesn't. So good. We can go home. Except that this is a bit of a scary conclusion to reach, right? If I'm the one driving that car, would you really be so sure that you're not hitting the surface? Point cloud reconstruction is an underdetermined problem. We don't actually know what the surface looks like. There are many possible surfaces. Sure, it could be exactly like Poisson reconstruction claims, but it could be like this. It could be like this. It could reasonably be like this, or even like this, right? There are many possible surfaces because this is an underdetermined reconstruction problem. Some of them won't intersect the car, but some of them will, right? In a way, Poisson reconstruction is projected to only one likely surface and ignoring the rest, and giving us an answer like, no, it doesn't. In this work, what we do is we formalize this statistical understanding of the many possible reconstructed surface and give more complete answers to this question. This will not just be useful for this collision detection example. I'll show you later that it's useful for things like ray casting, next view planning, and point cloud repair. So how do we do this? Well, we do it through Geometry Plus, specifically through Geometry Plus statistical learning. We're going to combine a concept from geometry, which is Poisson reconstruction, with a concept from statistical learning, which is Gaussian processes. In a way, this is especially satisfying because these are, in a way, the two crown jewels of each field, Poisson reconstruction and Gaussian processes. So let's look at each of them, and then I'll show you how we put them together. Poisson reconstruction. All right, I'm going to explain you how this works. That's not making me nervous at all. So Poisson reconstruction has been around for a long time now. And I've been working on it for a few months. And I've been talking about it to people for a few months. And something I've learned is that most geometry or graphics researchers have a very clear, good idea of how Poisson reconstruction works. But surprisingly, it's different from one researcher to the next. So like they all have very clear, very determined ideas of how it works, but they're all different. And they're all correct. The problem is that Poisson reconstruction is such a germinal work that you see whatever you want to see in it. So if you're a PDE researcher, you would think that the cool thing about Poisson reconstruction, the real contribution is how it shows the reconstruction problem as a PDE solve. If you're a numerical analysis researcher, you'll think that this is about approximating an integral. That's what Poisson reconstruction is doing. If you're like me, you see it as an interpolation problem. And if you talk to a statistics person, Poisson reconstruction is just doing a supervised learning process. It depends on who you ask. So if you have an idea of how Poisson reconstruction works, which maybe some of you do, I ask that you put it aside for 5 minutes. It'll be back where you left it afterwards, but put it aside for 5 minutes because I'm going to tell you how I understand it. And that will help understand the rest of the talk. So here's how I interpret Poisson reconstruction. You start with an oriented point cloud, which mathematically is just a bunch of points and a bunch of vectors. And the first step is you do an interpolation. So you go from the vectors that are described only at some points in space, which is your point cloud, at a discrete set of points, you go to a vector field that you can sample anywhere in space. This vector field may seem like a lot of math, but all that this is doing is a weighted combination of the vectors in your point cloud. It makes sense that when you're interpolating something, you're doing a weighted combination of the data that you have. And the weights depend on this kernel here that just measures how close 2 points are. So it makes sense that if you're doing an interpolation, points that are closer have a much higher effect than points that are far. So that also checks out. Even if the math can look scary, this makes sense. There's also this term that's measuring the local sampling density. I'm not going to go into why we need that, but if you think about it, it also becomes obvious why you would need to normalize that by that. So in the end, this formula we can write as a matrix multiplication like this, where D is a diagonal matrix of local sampling density. Once we have this vector field, which we can sample anywhere in space, so it's a vector field function, we solve a partial differential equation to get the scalar field that has this vector field as its gradient. That's how I understand it. And this is a Poisson equation, so this is why it's called Poisson surface reconstruction. But even if this is the part that gives it its name, it's not the part I care about the most. The thing I care about is this equation, this vector field interpolation, because the punchline a few minutes from now is going to be that this equation is the same as the mean of a Gaussian process. So really, all you have to take from this part is that Poisson reconstruction interpolates a vector field that has that equation and then uses that vector field to get a scalar field. So let's look at what a Gaussian process is. To put it in a way that's trendy today, a Gaussian process is a way of doing supervised learning. That doesn't really mean anything, and I'm a mathematician, so I'm going to need a bit more than that. Let's look at what that actually means. It means that there's some function u of x that I don't know, and I want to know what this function looks like. I sometimes like to work with examples, so I like the idea of u measures how long your advisor is going to take to respond to an email. And x can be the time of the day that you send the email. That's the one I like to imagine. The first thing you do is you come up with a prior. This is given in the form of two functions called the mean and the covariance, but you don't need to understand what this means. Basically, this encodes the knowledge that you have of this function before you see any data. So, you're emailing your advisor for the first time. How long do you think it's going to take? Maybe a day, 2 days, a week? This is encoding that type of knowledge. And you may think, well, maybe if I email him at 2 a.m., it'll take longer than if I email him at 3 p.m. That type of knowledge is what's encoded in the prior. The next step is we observe some data. So we send a few emails and we log how long it takes for them to respond. That's basically a bunch of samples of this function u at some times x. The cool thing about Gaussian processes is that once we've observed the data, we have a posterior distribution for what the function looks like at the unobserved at points that we haven't observed. So if I sent him an email at 2 p.m., he took however long to respond. I sent him an email at 4 p.m., he took however long to respond. I can ask, how about 3 p.m.? I haven't tested this time, but the Gaussian process will give me a mean and a variance for, how much does the Gaussian process think that he's going to take, and how sure is it about that guess? And we don't need to actually sample any function to do this. The Gaussian process will give us this mean and this variance with a bunch of matrix multiplications. So it's a closed form mean and a closed form variance. So this is what every Gaussian process looks like. It starts with a prior, it observes some data, and then it gets a posterior distribution for the function with some mean and some variance that you can easily compute with matrix multiplications. I'm going to do a few simplifications on this. The first one is a very common one for Gaussian processes, which is we're going to assume that the mean is 0, like this. That might sound weird because obviously my advisor does not take 0 time to respond to me. I wish. But this is actually trivial to do. This can be done with a loss of generality because you can always take the Gaussian process plus something. You can always add a constant. So assuming that the mean is 0 is a way of simplifying everything without actually losing generality. And one thing it simplifies is this equation, which becomes this. So that makes it easier. Now, if you're a math person or a numerical analysis person, you might be looking at these equations for the mean and the variance and thinking, well, that doesn't look as easy. Seems like you're doing a matrix inversion or a linear system solve. Is that hard to do? I wonder the same thing. So I looked at what this matrix looks like. It looks something like this. It doesn't look exactly tri-diagonal, but this is like a 1D version of the matrix. What I initially saw about these types of matrices is that they're very sparse. So most of their entries are 0. The diagonal element is the highest element in the row. It's the same for every row entry, for every diagonal entry. And the rest of the elements are positive, but very tiny and they're tinier the further two training points are from each other. So I stared at this matrix for a while, and I realized I've seen this kind of matrix before. This is kind of like a finite element mass matrix, if you've worked in finite elements, or like a finite difference mass matrix. Because all the entries are positive, it's mostly sparse, it has high diagonal elements, it's checking out. And for finite elements, we usually also don't want to have to invert this. We do something called lumping. We take the matrix and we turn it into a diagonal matrix. This is something that we can do in finite elements in a very recent way, and there are proofs showing when you can do this and when you can't. So I thought, let's do the same thing. Since this kind of looks like that, let's do that. So I call this matrix D, and I just plugged it here. Now I realize that this is not the most mathematically rigorous way of explaining a step in an algorithm. So you might be wondering, how legit is this lumping? The answer is, it's sort of legit. It's valid under some assumptions. So in the paper, we show that there are some cases, some limits where it holds. But actually, I added this because 2 weeks ago, there's this other paper that came out on Archive that basically shows a smarter way of doing this. So if I were writing this paper now, I would use this. But since this didn't exist back then, I had to use this lumping that's probably slightly less or mathematically less rigorous. I actually met with one of the authors of this paper, and they weren't very happy about my lumping. That question?
Yeah, just a quick question. The matrix that you had before, that is the mass matrix with respect to sort of delta functions at your samples.
Yes,
Right?
basically
So
that.
It really is a mass.
It really is a mass matrix. It's just that, yeah, because it comes from evaluating the kernel, basically. Yeah, the thing is that we're not solving a physical problem on it, so we can't like justify lumping in the same way that you do in finite element. So it is a mass matrix. It's just not like used in the finite element sense. So that's why it's less rigorous. So we would use this, and if what is it, like November 17th, if you want to write a SIGGRAPH paper for January 25th, an easy one is to just plug this into what I did. You can do it in 2 months. I'll release code for this, and it'll be fairly easy to do. They also release code, so it's just about plug into thing. Right. So anyway, let's not get distracted. We have this Gaussian process is what we're doing, and now we have D as a diagonal matrix there, which is easy to invert. So mathematicians won't complain anymore. The last thing we're going to do is I give you this example of a function of how long does my advisor take to respond to an email. That's a scalar function. It's measured in seconds, minutes, hours, weeks sometimes, but it's a scalar. But really, the same thing we did with a scalar, we can do for a vector, right? So we'll just have 3 coordinates. Each of those coordinates is a Gaussian process, and the mean will also have an arrow on top of it. It will be a vector. So this is where I wanted to reach. A vector-valued Gaussian process with a lumped covariance matrix and a 0 mean prior. That equation is exactly what I promised. This is exactly the Poisson reconstruction vector field. So this was our aha moment. This is what we realized. We realized that under some assumptions, a Gaussian process's mean was the same as the Poisson reconstruction vector field. So this is the major mathematical realization. Everything we're going to do from now is about exploiting this. Now that we know this, we can think, well, what if Poisson reconstruction had wanted to do a Gaussian process from the start? We can reinterpret Poisson reconstruction as a Gaussian process. And this is what we did, and we call it stochastic Poisson surface reconstruction. So let's do just that. The point cloud that we had, the input, it's no longer just a bunch of vectors and points, the output of a 3D scanner or something like that. No, it's samples from a statistical distribution. That's Gaussian. The interpolation step that we had before is no longer an interpolation. It's a Gaussian process. with a given prior. And that doesn't give us a vector field. It gives us a vector field posterior distribution. What does this mean? It means that for every point in space, I no longer just have one vector, which is a vector field. Vector field means for every point in space, I have a vector. Now I have a vector field distribution. So I have a bunch of vectors, and each of them have different probabilities. So that's what I have for every point. Now, the next step in Poisson reconstruction was to solve the Poisson equation. And that was a PDE that was described in the space of functions, but we can solve it in the space of distributions too, and get a posterior distribution for the Poisson reconstruction scalar field. What does that mean? It means for every point in space, we have a mean that looks a lot like the Poisson reconstruction output, but we also have a variance that measures how sure we are of that value. And these two will fully determine a Gaussian distribution for what the scalar field is at that point. I thought this was very mathematically interesting. Okay. This Gaussian distribution is fully determined by that mean and that variance. And if I change the point, I'll get a new mean and a new variance, which will give me a different Gaussian distribution. As you'd expect, points that are close to the data, or in the reconstruction language, points that are close to other points in the point cloud will have very tiny variances, or will be very sure of what the value at these points looks like. But points that are far from the data will have higher variances. So I'll be more uncertain of what the value at that point looks like. This is a very powerful quantity to have, this whole statistical distribution. We can compute many statistical queries on it. So for example, one thing we can do is we can calculate this integral. This integral, since it's a Gaussian, if you've done if you've taken a statistics course, this integral can be sampled very easily, and it's just the probability of the function being below 0. But this is the Poisson reconstruction scalar field. Being below 0 means being inside the shape. So this is the probability that a point is inside the reconstructed surface. And we can plot it for every point, and it'll look something like this. So now we formalize this statistical understanding that we started with of there are many possible surfaces. Now we have an actual probability field that measures how likely each point is of being inside the reconstructed surface. I'm going to keep using these simple 2D toy examples, but we can get these quantities in 3D as well. Now, why is this quantity, this probability, so useful? Well, one thing we can do is if we show it for many different shapes, you can see that it somehow intuitively measures how good our reconstruction is. So for the thing on the left here, I still have no idea what the surface looks like. But for the thing on the right, I'm pretty sure what it looks like. So it's easy to see that one is more uncertain, one is less uncertain. This is because one has values that are almost either 0 or 1. It's very binary, whereas the other one has many values that are near 0.5, which means that we don't know either way. So we introduce this thing called the integrated uncertainty that just measures how far you are from 0.5 in the probability. And this is a quantity that measures the quality of the reconstruction and goes down as we add more points. The cool thing about this quantity is that it's agnostic to what the actual surface that you're reconstructing is. So we can use it as a stopping criterion. For example, we can threshold it for different scanning procedures from different randomly sampled positions. And if we use the same threshold, we get similar quality reconstructions because it measures reconstruction quality. Okay, so that's one thing that we can do with this new statistical formalism. Here's another one. Ray casting against an uncertain geometry. So a similar question to the car one that I asked before is, where does a ray hit the surface? Of course, there are many possible surfaces like we covered. So the answer can't just be here, right? The answer has to be statistical distribution of where the ray may hit the surface. And this statistical distribution is actually hard to get just by looking at the point cloud. But fortunately, we have this map, this probability distribution, which we can interpret as the differential probability of a ray terminating. This is the trick that people do in volume rendering all the time. They say, oh, I'm shooting a ray through a cloud, So I'll look at the density of the cloud, and I'll treat that as the probability of a ray hitting a particle. So this is actually very legitimate. It's a differential probability. We can use that differential probability to compute the transmittance, which measures how likely is one ray to travel this far without hitting the surface. Is that a question or just a?
Just a quick question.
Sure.
Does this assume that probabilities of ray intersections are independent? Because it doesn't seem like it should. But it seems like this model sort of by accumulating says.
This assumes that they're independent.
But they shouldn't. Like if you're not certain on one area, you're probably not certain of the other.
That's a good question. You mean through the ray? So like the points through the ray are different. I don't actually know if we can assume this or not. That's a good question. We could add like correlations because we get a full covariance. So like we could add correlations between them. I do wonder what people do in volume rendering. Oh, wait, I just talked to someone at Dartmouth. Sorry?
Of measurable opacity, that accumulates.
Yes.
But this isn't opacity. Oh.
Well, the thing is like, so okay, this is something I've thought about for a while. People in volume rendering have a measure of opacity, and then they do this like weird thermodynamic trick where they say, let's treat this measure of opacity as a probability, differential probability of a ray hitting a particle, right? So in a way, what I'm saying is that we get directly that probability. I would need to think about this more. I hadn't, yeah, maybe we should account for correlations here. I'm not sure because these are marginal probabilities. I think when you do it through a volume, you would get the same problem where maybe if you hit a particle here, you're less likely to hit it afterwards. Yeah, I see that it's trickier. Yeah, good point. Anyway, we can compute this transmittance and sample from it to get the statistical distribution that we wanted before. So this is an example of ray casting. This is of course a very simple one, but we can do it for more complex ones. So I took this spaceship. I took a virtual scan of a spaceship. You can see that the left side has more points than the right side. And I placed two cameras, one aiming at the place with the most points and one aiming at the place with the least points. We compute this same field and we simulate rays that hit against the surface, and we see that the ones from one camera are obviously more certain, whereas there's a wider spread for the ones from the camera that's aiming away from the data. So anyway, why do we want this? Well, I wanted to do this because we can combine it with the integrated uncertainty that we showed before for next view planning. So say you have a point cloud of something that's incomplete, and you want to know where you want to scan next. Something you can ask is, how sure am I of the reconstruction now? So what is my integrated uncertainty now? Then I can place certain hypothetical cameras. I can cast rays from those cameras and sample new surface points. And I can ask, once I've added this point, how did the uncertainty change? So how better did the reconstruction get? And this lets us score many cameras according to how good they would be as the uncertainty reduction next view for the scanning. So anyway, these are all things we can compute thanks to this quantity, this integral here. But there are other statistical quantities that we can compute. So for example, there's also this thing. This is a quantity that is proportional. It's not exactly, it's not normalized, but it's proportional to the probability of a point being on the surface. So not in the shape, but on the surface. It's similar to the previous one, but not exactly the same. I think this can be used, for example, for many machine learning approaches where you want to sample near the surface, but during training, you don't know where that surface is. So I think that's a possible use for this quantity that I thought of a few weeks ago. So it's not in the paper. In the paper, we actually pitch it as a way of doing point cloud repair. So if you have a shape and you simulate a scan of it, well, you can use these probabilities as the probability to sample more points from, and that way you can fill out the missing chunks of a point cloud. So this is another statistical quantity that we can use for a novel application of Poisson reconstruction. You might be asking, what about the car? Does the car hit the surface or not? Well, we can answer this type of question, but we need something else. We need regional probabilities. Basically, they're an extension of this map. This map, like we were talking about before, does not account for correlations between points. So maybe one point has 0.5 probability of being in the shape, another point has 0.6. But if the 0.5 point is in the shape, then the 0.6.1 is also in the shape, right? So there can be correlations between points to account for those. We can account for those and compute regional probabilities. So like we draw a whole region in space and we account for the joint probability distribution of that whole area, and we can ask what their probability of intersecting the surface is. And this is exactly what we need for examples like the car one. So I constructed this very realistic street scene, and I placed a car, scanned its surroundings, and it can compute its collision chance along a given path. So this sort of answers the question of the car. You can imagine that Poisson reconstruction would just tell us no collision, no collision, no collision, yes collision. Right? We are giving much more information. I don't think I would be comfortable with a 36% collision chance if I were driving the car. So anyway, you might have heard of this saying that actors do one for you, one for me. Like they'll do a movie like The Avengers that sells a lot. They don't like doing it, but they'll do it because it sells a lot, and they'll use that money to fund the movie that they really want to do because they like it, but maybe it won't sell as much. These are the applications that I did for the reviewers because I wanted to get a SIGGRAPH paper. But what's the application that I liked for me? So the thing I liked was the fundamental contribution of understanding Poisson reconstruction as a statistical process. And once we've recall that to get the exact formula from Poisson reconstruction, we needed to assume a specific prior in the form of a specific covariance, and critically the mean zero prior that I told you about. But now, you know, sure, we could assume those and get the Poisson reconstruction formula. But dare I say, now that we understand it in this way, can we do better, right? Now, Poisson reconstruction isn't some tradition passed down by generations, that this formula that we repeat to our children and their children. It's actually a statistical process. Now we understand it in a new light. So now that we have this understanding, can we do better? Specifically, can we change these priors depending on what the reconstruction we're doing is? So a very known limitation of Poisson reconstruction is that it sometimes produces open surfaces, even when obviously the thing that you represent, that you're reconstructing, is known to be closed. You know, if you're a Tesla and you're scanning your surroundings, you know that the car that you're scanning is a closed surface. There hasn't been an infinite car yet. And from the looks of it, it doesn't look like Elon Musk is going to invent it anytime soon. So this is a problem with Poisson reconstruction. It outputs open surfaces. And there have been whole papers on how to solve this, how to impose constraints on Poisson reconstruction so that it outputs closed surfaces. With our statistical understanding, we can actually add this in less than a line of code just with the prior, by changing the prior and making it spherical. And that way we enforce legally that the surface has to be closed. We can not only do it for simple 2D examples, we can also do it for very simple 3D examples. So in this case, we do a limited scan of an apple. If we use vanilla Poisson reconstruction, it would look something like this, which looks like the Plant vs. Zombies evil guy. I don't know if you've played it. Once you've seen that, you can't unsee it. So obviously, there are no open apples. And if we use our prior, we get this, which is closed. And we can also have a variance map that tells us which parts we're more or least certain about. An apple is a very simple example, but we can even, with very simple priors, we can also use them for more complex geometry, like this car, where we also do an incomplete scan. This is the Poisson reconstruction output, and this is ours. So this is already much closer to the ground truth car than the Poisson reconstruction output, and this is using a very simple geometric prior. I told the method cars are roughly ellipsoidal, which obviously is not what a car looks like. It's just a very, very crude approximation. So imagine if this is already this good, imagine how good learned task-specific priors would be. So instead of if I told the algorithm cars are roughly ellipsoidal, what if I told the algorithm, here's 1,000,000 cars, I'm going to sample a new car? That, I imagine, could be incredibly powerful. So I think, yeah, a very exciting avenue for future work is task-specific learned Poisson reconstruction. So we use this prior, this statistical knowledge, and make the prior be task data dependent. And I think that's a very promising avenue for future work. Another avenue for future work that's kind of a sad one to say is we'd like to improve the runtime of our algorithm. So getting the mean, we can actually do pretty fast, but computing this variance is very slow. You may be asking why. The reason is in this solve PDE step that I haven't told you much about. I didn't tell you much about this because it's boring. Or rather, it's not a boring step. The way we do it is boring because we just set a grid and this becomes two linear systems. So there isn't much meat there. The linear system for the mean is one linear system of size m cubed, where m is the size of the grid along one direction. And that we can do pretty fast. That's basically the runtime of the original Poisson reconstruction. But the variance is a matrix equation. So it requires solving m cubed linear systems of size m cubed, which is m6, right? So this is impossible. M6 in graphics means infinite. So this is very, very slow. And to get around it, we do a classic computer graphics trick, which is we're going to project to a subspace. We're going to do the subspace of a bunch of Laplacian eigenfunctions. And we're going to solve this equation in the reduced subspace so that it's faster. And with this trick, we take it from very slow to slow. So, it's nothing to laugh about because it's, at least we make it manageable. Slow means that we can run it. Very slow meant that it wouldn't even run. But it's still a bit disappointing because this is a very simple function, right? This doesn't look like a fractal. This looks like something that could be easy to approximate, right? So a very immediate avenue that we hope we do as a follow-up is how to approximate these functions. Now the problem is just about approximating these functions. When you manage to approximate them, you can use our work to give you all the statistical formalism. So again, 2 months and a bit, you can write a secret paper on this too. Here's another idea we have. This comes from a question that I get every time I give this talk. I get this question by someone who says, well, couldn't you just do all of this with a neural network? That's a question I get every time. I never know what to answer, so I look bad. But so I thought I would preempt it, add a slide for it, say it's an open question, and then I no longer get that question. I no longer look bad. But I've gotten this question so many times that I started looking into it. How could we get something similar to what we did, but with a neural network? And there are these things called Bayesian neural networks that at least claim to output an uncertainty measure that is similar to the one that we output. So if there's a way of doing this as a neural network, I think Bayesian neural networks are the way to go. I haven't looked into it more than that. More broadly, what we did here is we took a classic geometry algorithm, which is Poisson reconstruction, and we looked at it as a Gaussian process. So something I'm excited by is what other parts of geometry processing can we understand as Gaussian processes? So what I'd like to convince you to do is look at the workflow that you have, see if there's any point at which you're solving something that sounds like an interpolation. So you have some discrete set of data and you're sampling between the data that you have. And think if you could plug a Gaussian process there. If you could change that for a Gaussian process, maybe you can quantify the uncertainty of what you're doing, not just get a simple scalar output. More broadly, be it with Gaussian processes or with neural networks or whichever way, our method falls into combining geometry with uncertainty quantification. And this is exactly what I'm working on now. My dream is a fully uncertain geometry processing pipeline. And there have been some works quantifying uncertainty in geometry processing, but like ours, they're all limited to the capturing step, mostly. This makes sense because capturing is when I have incomplete data, when I have measurable noise that I understand. So it makes sense that most of what we've done so far stays in the capturing realm. But then we don't do much with those stochastic captured objects. I think something I'm trying to work on now is carrying that stochasticity through the geometry processing pipeline. So, okay, we captured an uncertain shape. How do we do uncertain discrete differential geometry on it? Or how do we do uncertain numerical analysis on it, right? Let's not just stop at the uncertain capture shape. Let's carry that all over the pipeline. And this won't just be useful in its own right. It will be useful because it will let us inform the capturing process. So if I'm sampling something, and all I care is about some differential probability of something, then maybe I can quantify the uncertainty of that differential probability, and that'll tell me where to scan next. Of course, this is a bit of a pipe dream, and this work is only one step in the pipeline towards this vision. And one of the reasons that I'm here today is that I think we together could do the next steps. So I'm going to end by pitching a few projects that are free. Free as long as we do it together. So, terms and conditions apply, but you can grab any of these projects that I'm going to say now, grab them, we'll work on them together, and you'll be the first author, you'll do all the coding, but I bring this idea to you. So the first one I told you about is how to approximate these variances faster. We can plug that into our method. I can give you the code that we have right now. You just write that function that approximates that thing, and we're done. And we have a SIGGRAPH paper. We can even have it before Christmas, I think. We can enjoy the holidays. Another one, learn task-specific priors. All you would need to do here is to learn vector fields for different shapes. So that we can plug that in as the prior for the reconstruction. So I'll give you the rest of the code. All you need to write is a function that says project a given car reconstruction into possible vector fields of cars. I think that's pretty easy, and we could call it task-specific Poisson surface reconstruction. And my understanding is if you have Poisson surface reconstruction in the name, you can't get rejected. So that would be another SIGGRAPH paper that we could write together. Another one would be more Gaussian processes. This one depends more on you, but it basically find the point in your pipeline where you use an interpolation, turn it into a Gaussian process, and we can write a paper about that. I'll lend you all my Gaussian process knowledge, and you can teach me about whatever it is that you're doing. These are three simple projects that I think are promising. I have a decent idea of how to do them, but I also have some that are more open questions that we could work on. We may not make it to the January 25th deadline, but I think the payoff is also bigger. So if you want to work on these, also reach out to me. Here's one. So in this work, we took a point cloud as input. We didn't care about how we got that point cloud. That was our input because we're computer graphics researchers. We usually take point clouds as the input in our process. And we got a probabilistic surface. I think a promising avenue for future work is to combine this with the uncertainties that we get from specific 3D scanning techniques. So here's what I mean. There are all these papers in computer vision, so the people that are, next door, where their input is the real world. And they do some uncertainty-aware 3D scanning, and they output point clouds or depth scan with quantified uncertainty. There are algorithms like this already. And then there are algorithms like ours in computer graphics, where our input is a point cloud, and we quantify uncertainty of the reconstruction. Weirdly, we never talk to one another. So I think a promising avenue for future work is to do this arrow that goes from one to the other. Basically, instead of taking an input point cloud, let's take a specific input point cloud, which comes from a specific 3D scanning techniques. And instead of assuming that it's a Gaussian, like I did in this work, let's take specifically what is the uncertainty, the experimental uncertainty that we got from that point cloud. That's, again, an exciting avenue for future work. If you're in computer vision, we can work on this together. If we're in computer graphics, we can find someone from computer vision to work on this together. Here's another idea. So we came up with these probabilistic surface representations that quantify this intuitive understanding of there are many possible surfaces. A question I have is, how do we do numerical analysis on these uncertain surfaces, or on all of them at the same time? I wouldn't know how to answer this, except that lately there was this work called Monte Carlo geometry processing, where they basically solved equations by taking random walks from a point inside the shape and waiting until they hit the surface. They call this walk on spheres. Well, we have something like a surface. We have a probability of being on the surface. So I thought, how about we do walk on spheres, so like this Monte Carlo geometry processing algorithm, but then stop according to that probability instead of hitting the surface. So that's another paper that we could write together. And I mean that this is not just like a pitch that I'm making. I believe that. Hopefully I've convinced you of this geometry plus vision. And if any of these projects sound good to you, you can find me here. So find my email there, email me. We can work on one of these things together. I'd like to end by thanking all my collaborators from the past 3 years. Your picture could be here if you send me an email. So thanking all of these people that I've had the pleasure to work with, and thanking all of you for listening to me today. Thank you.
We have a little bit of time for questions if people have them. Otherwise, I'll ask them.
Oh, no.
I have a quick question regarding the uncertainty calculation for next best field selection. Are the point clouds in that well, are the points in that point cloud assumed to be just given by default, or because in reconstruction you could, I'm assuming you can, of course, as we talked about, project the uncertainty from the camera feed back into the 3D space. So was that included in the next best field planning, or is it just assume that the points exist and they are down?
Let's clarify the question you're making. So you're saying the input point cloud, so like the one we have before we consider the question, is that one assumed to be the ground truth?
Yes.
No, that one is assumed to be the current scan. So it has its noise. We're assuming that it has some Gaussian noise. So we're assuming that that one's noisy. So that's happening at the middle of the scan.
So it's assumed that it's a scan and not a reconstruction from 2D space in the first place. That would consider.
That's right. It's assumed that it's 3D points that you've gotten through your scanner. I mean, we're broader than that. It's assumed that it has a Gaussian noise. We don't actually care. Maybe you did some fancy machine learning that gave you a Gaussian noise. That's what we're assuming.
Thank you.
Yeah, thank you for the question. Yes. Okay.
So after learning the idea to concept of complexity, so as we can, is it possible to add experiment to the complex structure to now have more information, then we can decide reconstruct the part wrong.
Yeah, that's kind of what, okay. So the question is, I'm going to repeat it because I don't know if the mic catches it. The question is, can we use this probabilistic understanding to sort of rectify things that we've done on the fly? So like we scan again, we learn something about what we had before, and that improves what we had before. And yes, like we definitely can do that. And you know, if we sample again a region that we sampled noisily before, having more samples will make us more sure of what the distribution looks like in those areas. So like we can always incrementally sample and gain more information about the shape. Yeah. So that's kind of what I wanted to show in the next view planning example. You have a current scan, you scan again, and you learn more about what the shape looks like.
Quick question. You showed an example of collision detection from SPSR, but you also did collision detection with flat model.
Yes. Well, the swept volume one assumes that the surface is certain. So that's one where you're the one modeling the shape and you're 100% sure of what it looks like. So you'd use a different one depending on the application. That's a good point. Yeah, I didn't realize that I had done basically the same thing twice. It would be interesting, actually, to say, what if I'm certain about what the shape looks like, but I'm uncertain of what the trajectory is? That way, I can have an uncertain swept volume, and then the problem would be like this. Then we would do it with like probabilistic collision detection. So yeah, I guess the question is, it depends on the test, but you're just making me think of a fun way of combining them.
Maybe one last follow-up.
Sure.
Because you did talk about computational runtime, I was just thinking, what's the computational runtime? So say for the race car example in 3D space.
How long it took?
Yeah, for the computation of variance, uncertainty.
Yeah, it's a trade-off between how fine you want your grid to be and how accurate you want it to get and how fast you want to have it. So like our specific examples all take around 2 or 3 minutes to run. We do it on 100 by 100 by 100 grid. We don't do anything smart about the grid. I mean, I don't want to dismiss that because I know that there's a lot of people doing very smart things to compute basically the same Poisson problem, but faster with an octree, with multi-grid in many different ways. We sort of treat those as orthogonal. In the end, we get a Poisson equation. You can plug in your favorite very fancy, fast Poisson solver. So like we could do this faster. We just were happy at the resolution we were working. And we didn't want to get into the weeds of how to solve it, which is a way of, I didn't want to have to figure out by hand how to solve an integral. That's basically what happened.
This is very interesting. If you're, maybe I missed this, but if seems like I could get a significant speed up with solving things incrementally.
Okay.
Have you looked at that? No?
So you're saying like I add a new point instead of having to do the whole.
Yeah, exactly.
Yeah. It's strange to think about if this was just a Gaussian process, it would be trivial.
Right.
But we're doing the Poisson solve later, so that is global. So you can't say
you have this probability field.
Yes.
And if you think about it from the Gaussian process point of view, right now get some observations with maybe an independent uncertainty attached to it. I should be able to see how that field is constrained.
Yes, that's true up until the Gaussian process. Like that's up and including the Gaussian process step. So like if you're just looking at the vector field, we could do that incrementally, add one and very quickly leverage all the computation that we're done and have it be like constant time or like constant time when you add a new sample. The problem is that then you have to use that vector field to solve a Poisson equation, and that part I don't know how you leverage. Maybe this sounds like a Misha question. Maybe there's some way of saying I've solved a Poisson equation for a vector field that's very similar. How much computation do I actually need to do to solve a Poisson equation for an input? I don't know.
There are some very practical uses of what you're talking about. There's time later. I can chat with you.
Yeah, that'd be great. I'd love to.
I think we're about to get kicked out of the room. Are there further questions? All right, Silvia, thank you so much.
Thank you.
That was really a great concept.
Oh, thank you. That means a lot. Thank you.
Here for a while.
You don't look it. You don't look like you've been here.
Well, I spent the first half of my career at IBM.
Oh, wow.